Welcome back to the Deep Dive. This is the show where we dig into all those complex, nuanced details that are usually buried in research papers, and we try to turn them into sharp, actionable knowledge.
And today, we are standing right on this fascinating line where massive general intelligence meets the very messy, very specific reality of an individual human being.
Exactly. We got this question from a listener that really hits on a core engineering problem. If you fine-tune a powerful automatic speech recognition model, an ASR model, like whisper to your own unique voice,
Yeah.
Your accent, your cadence, your specific vocabulary, how long does that actually last?
It's such a great question because it gets at the heart of stability over time. And this isn't just a theoretical issue for our listener. They mentioned having a distinct Israeli English accent.
Right, and they use a lot of specialized technical jargon. And here's the kicker. They frequently code switch, so bouncing between Hebrew and English, sometimes in the middle of a sentence.
We do something a general model just completely falls apart on.
Constantly. So the mission for this deep dive is really about that long-term stability. If you put in all the effort to fine-tune a model today, does it degrade over time? I mean, our voices change, right?
They absolutely do. We get older, we catch colds, our stress levels can change our pitch. Even our speaking rate can shift subtly over years. So does that mean we need to be continuously retraining, feeding the model these little updates every few months?
Or is that initial fine-tune robust enough to handle those natural, gradual fluctuations of a human voice? That is the ultimate trade-off, isn't it? The model's massive general knowledge versus the hyper-specific truth of one person's voice.
So over the next half hour or so, we're going to unpack all of this. The technical legitimacy of personal fine-tuning, how those small updates actually work with a model that's been trained on, 680,000 hours of audio?
And most practically, what deployment strategy gives you the best custom accuracy if you want to run it all locally on your own hardware? So let's start at the very beginning. Why is this personalization effort even worth it from a technical standpoint?
Oh, it's absolutely worth it. I'd say it's more than legitimate. It's quickly becoming the standard for any kind of professional user. A general model, I mean, no matter how powerful it is, it's always optimized for the average human voice.
Speaking standard language.
Exactly. So if you fall outside that average in any significant way, your word error rate, the WER, it just climbs fast. Personal fine-tuning is what corrects for all those individual outliers.
So let's detail some of those voice characteristics that really matter, because I think a lot of people assume, hey, Whisper is multilingual. It should handle my accent and my language mix just fine.
Right, but the data shows that ASR performance is sensitive to things that are incredibly granular. It goes way beyond just a broad regional dialect.
Okay, so where do we start?
Well, they are incredibly sensitive to nuance.
Right.
Let's start with maybe one of the biggest challenges for transcription, speaking cadence and rate.
How fast or slow you talk.
Most of the training data that these models see, it kind of hovers around 140 to 160 words per minute. If you're a fast speaker, say you're pushing past 180 words per minute, you start to introduce a high degree of what's called co-articulation.
Co-articulation.
Yeah.
That's the blending of sounds across words, right? Like when did you becomes did ya.
Exactly that. The little phonetic markers that separate words, they start to disappear. And that forces the model to rely way more heavily on its language modeling, its internal knowledge of which words are likely to follow each other, just to figure out where the boundaries are.
So if you're rattling off very specific technical terms at 200 words per minute, the model is dealing with both blurred boundaries and words it almost never sees. That's a double whammy.
It's a huge problem for it. And conversely, slow speakers, so people under 120 words per minute, they cause a totally different kind of issue. Those long pauses between words. The ASR's internal system often misinterprets them as the end of a sentence.
So you get these fragmented transcripts with punctuation all over the place.
All over the place. And just variability in your pace is a challenge, too. The models really prefer consistency. So if you start a thought slowly and then speed up as you get into a dense technical point.
The model has to constantly adjust its internal clock and its boundary definitions, which, okay, that's going to introduce errors right away.
Immediately. Okay, so next up we have vocal dynamics. This is basically your pitch range and how much your loudness varies.
And I'd think a huge model like Whisper has seen it all, right? Children, men, women, all different ages.
It has. It's very robust. But if your pitch range is significantly different from the demographic it was most heavily tested on, it can still struggle. The more common issue, though, is specific vocal habits. For instance, vocal fry.
That sort of creaky voice you sometimes hear at the end of a sentence.
Right. When that's used habitually, it can really confuse the model.
Why, though? Does it just sound like static or noise to the AI?
Often, yes. The spectral energy distribution of vocal fry, that low rattling sound, it's very inconsistent with typical voiced speech. So a generalized model might hear that and think the speech is ending, or that some background noise just crept in.
And it might just cut the transcript short or
Yeah.
misclassify the sound entirely?
Exactly. So if you as an individual use vocal fry on a regular basis, you're creating this unique personal acoustic pattern, and that pattern needs fine-tuning for the model to learn how to correctly map it to actual words.
That makes perfect sense. The model is just optimized for clean, consistent energy. Okay, what about articulation clarity?
This is a critical point. If you're a user who speaks very clearly, very precisely, you actually require less model capacity to get a good transcription. The acoustic signal is just clean and unambiguous.
A lot of us speak casually. We mumble, we drop vowels, a lot of gunag instead of going to.
Right. And that ambiguity requires a much, much larger model. Often you have to jump all the way up to the biggest sizes like Whisper Large V3 just to deal with the sheer variety of ways a single word can be pronounced sloppily.
So basically, if I mumble, I need a bigger brain in the AI to clean up my mess.
That is the perfect way to put it. And finally, let's touch on prosody. This is the melodic part of your speech. The intonation, the rhythm.
How you say things, not just what you say.
Exactly. And prosody is often the key to disambiguating words that sound the same, homophones. If you speak in a monotone, for example, the model loses that crucial rising or falling tone that usually signals a question versus a statement.
And I've heard of uptalk, where people have a rising intonation even on statements.
Yeah, that can trick the model into putting a question mark where a period should be, which can really mess up the readability of the whole transcript. Fine-tuning teaches the model your personal acoustic signature across all of these different dimensions.
Okay, let's pivot to the two areas where general ASR models go from just struggling to, well, outright failing. This is where the case for personalization becomes undeniable. Code switching and domain-specific terms. So our listener mixes Hebrew and English. Why does a state-of-the-art multilingual model just suddenly break down when they use a Hebrew word in the middle of an English sentence?
It's a great question. It's a common confusion. The problem isn't that Whisper doesn't know Hebrew. Of course it does. It's that it doesn't know your personalized way of switching between languages.
Okay.
See, Whisper is typically trained on these huge monolingual data sets. When you start a transcription, you usually tell the model the primary language is English. So the model is now operating under this really strong assumption that the words that follow are going to be English words.
So when a Hebrew word like, what was the example, makolet?
Right, for convenience store.
When makolet appears, the model is still completely locked into its English acoustic space and its English language model.
Correct. And the general model has two ways it can fail here. The most common one is what we call phonetic forcing.
It forces the sounds into English words.
Exactly. It tries to map the Hebrew sounds to the closest English subword units or tokens it knows. So makolet might come out as maculate or mock-a-lot. The phrase is acoustically similar, but it's semantically complete nonsense in the context of the sentence.
And the second failure mode.
The second one is less common, but it's worse. It's a flow breakdown. The model detects a huge linguistic outlier. It might try to switch to its Hebrew language model, fails to reconcile the two grammars, and then it just spits out garbled text. Sometimes it just stops transcribing altogether.
So fine-tuning teaches the model to actually expect these specific switch points.
Yes. It teaches it to map the acoustic profile of makolet directly to the Hebrew token, even when it's surrounded by English words.
So we're essentially teaching the model a specific bilingual grammar that's totally unique to the user, not just two separate languages.
Exactly. And the very same principle applies to technical vocabulary. You know, if you're a programmer, you're using terms all day like gRPC, idempotency, cache invalidation, ROCM. These terms fail constantly in general ASR.
Why? What's the weakness there?
It's really a triple threat of weaknesses in the general training data. First, there's just weak prior knowledge. These terms are incredibly rare in that huge 680,000-hour corpus, which is mostly just common conversation. The model has very little confidence when it tries to predict them.
Okay, that makes sense. What's the second threat?
Homophone overlap. A lot of technical terms are acoustic homophones with really common words. The classic example is cache, which almost always gets transcribed as cache.
Or GNOME, the desktop environment, becomes GNOME or GNOME.
Yep. The model just defaults to the most frequent common word it knows, even if the context clearly points to the technical term.
And the third weakness.
It's the uncommon capitalization and formatting. Technical terms often need specific capitalization, like PyTorch, gRPC, CDA. This violates the typical English sentence structure rules that the model has learned, so it fails to format them correctly unless you explicitly teach it during fine-tuning.
So fine-tuning is what fills that domain gap. It turns these rare, ambiguous words into high-confidence predictions, but only within your specific linguistic universe.
That's it, exactly.
Now that we've established the technical need, let's get into the ROI, the return on investment. Our listener asked if a modest improvement in accuracy is really worth the time investment. But when we talk about word error rate, or WER, why is going from, say, 8% down to 5%? Why is that not a modest change at all, but a transformative one?
This is a concept called the usability cliff. It's all about the nonlinear perception of error. For humans, the tipping point for ASR usability sits right around that 5% to 7% WER mark. Above 10% ER, the transcription requires a significant cognitive load. You, the user, have to actively monitor the text. You're constantly pausing to correct mistakes, and it just fundamentally breaks your focus. The tool becomes actively annoying.
It goes from being a helpful assistant to a distraction that you have to babysit.
Exactly. So when you move from 8% ER, which is where a lot of users with strong accents or complex vocabularies might be with stock whisper, down to 5% ER, you've achieved a 37.5% relative error reduction.
Which sounds good, but what's the real-world impact?
The impact is exponential. At 8% ER, you're correcting, on average, 8 words out of every 100. At 5% ER, you're correcting 5.
So let's put that into our listeners' context. Let's say they're transcribing 2 hours of dense technical notes every single day.
Okay, so if we assume a typical speaking rate, maybe 150 words a minute, 2 hours is 18,000 words. At 8% ER, you're dealing with 1,440 errors. At 5% ER, you're down to 900 errors. That difference, 540 fewer errors you have to review and correct, that is why we call it a nonlinear leap. The system crosses this reliability threshold. It goes from acceptable to trustworthy.
You go from actively monitoring the text to just passively trusting it.
That's the real ROI, the reduced cognitive load. But we can even calculate the hard numbers on the time investment. So if the fine-tuning process takes, maybe 20 to 30 hours of effort collecting data, transcribing it, running training cycles.
Right. What does that payback period look like?
Let's be conservative. Let's say your personalized model saves you just 5 minutes of correction time per hour of transcribed audio, and you transcribe 5 hours a week. That's 25 minutes saved every week.
Which over a year is over 21 hours of time saved.
So you've paid back your initial 20-hour investment within the first year of heavy use.
That's a powerful validation. And that calculation doesn't even touch on the intrinsic value, less frustration, more trust in the tool, being willing to use it for higher states, things like drafting professional documents.
Exactly. Personalized ASR isn't a luxury. For a professional, it's a necessary optimization for productivity.
This brings us to the most insightful question from our listener, really the core of this whole deep dive.
Yeah.
The stability over time. We're fighting against this organic reality that our voices change. My voice is changing right now as I get older. If I fine-tune a model today, why can I trust that adaptation to still be accurate 3, 5, even 10 years from now? Even if my speaking characteristics shift a little bit without having to do continuous small updates.
This is where we get to really celebrate the genius of transfer learning and modern transformer architecture. The listener's concern that a small fine-tuning data set will just get overwhelmed or that the model will forget, it's a perfectly legitimate fear. But the architecture is designed precisely to handle this exact conflict. That initial fine-tune is extremely stable.
Okay, so let's define that paradox again.
Yeah.
You have this massive base model trained on 680,000 hours of the general population's speech. And you're comparing that to, 5 or 10 hours of your specific personal audio?
A tiny fraction.
How can that tiny amount of data update this giant model without destroying its vast general knowledge? That's the definition of catastrophic forgetting.
And the conflict is resolved by controlling the rate of change. The main safeguard against catastrophic forgetting is the strategic use of the learning rate.
And the learning rate, just to be clear, that's basically the dial that controls how much the model changes its internal weights based on the new data, right?
That's a great way to put it. It's how aggressively it adjusts its billions of weights. So during the original pre-training phase, the model used a relatively high learning rate. It had to to quickly sweep across that vast data landscape and learn the fundamental patterns of speech and language.
So pre-training does the hard work of building the entire map of human speech.
Yes. That initial process found what we call a good valley in the loss landscape. This valley represents a high-performing general model. When we move to fine-tuning, we use a learning rate that is dramatically smaller.
Very much smaller.
Often 10 to 100 times smaller than the initial rate. And mathematically, this small learning rate ensures that the fine-tuning makes only these tiny, highly specific adjustments to the existing weight matrix. We are not replacing the base knowledge at all. We are just nudging it.
So using that good valley metaphor again, the pre-trained model is already sitting in a deep, excellent valley that represents general ASR capabilities.
And the fine-tuning data proves that there's a slightly better nearby valley, a little local minimum, that is just perfectly optimized for your unique voice and your vocabulary. The extremely low learning rate acts like a mathematical tether,
Preventing it from jumping out of that stable region entirely.
Exactly. It just carefully descends into this adjacent personalized valley. This ensures that the new knowledge is purely additive and corrective. It's integrated into the existing structure rather than destroying it.
Okay, so that addresses the stability question regarding the size of the data. But how does that address the core issue of my voice changing over time? Getting older, getting a different microphone, catching a cold.
It addresses it because of the nature of the learning. The small adjustments we're making, they're targeting your personal patterns, but the foundational structure that recognizes human phones and general acoustics, the part that took 680,000 hours to learn, that remains almost completely untouched.
I see.
So even if your pitch drops a little with age or your cadence slows down, the model is still using that vast fundamental knowledge base. Your voice, even though it's changing, is still overwhelmingly within the spectrum of human speech that the model mastered during pre-training.
So because the fine-tune only added this slight personalized layer on top, it's inherently robust against those typical slow organic shifts.
Exactly. Continuous large updates are just not necessary.
This stability implies that the fine-tuning process is incredibly smart about where it applies its changes. It can't be updating all 1.5 billion parameters equally. So how does the model architecturally make sure that the foundational features, the basic ability to hear human speech, are preserved, while the specific features, like how I pronounce gRPC, get updated?
This is the genius of the encoder-decoder architecture in action. Fine-tuning is a highly selective process that really exploits the specialization of different layers within that transformer stack.
Okay, let's break down the layers then. Which ones are almost frozen, preserving all that base knowledge?
Those would be the early encoder layers, so typically layers 1 through 4. The encoder's job is to extract acoustic features from the raw audio, things like identifying basic phonemes, recognizing spectral patterns, handling noise reduction.
And my unique voice, despite my accent, is still fundamentally consistent with the training data at that basic acoustic level.
It is. Because the prediction error is so low in these layers, the learning algorithm calculates a minimal weight change.
And when you say minimal, what are we talking about?
We are talking exceptionally minimal, often just 0.1% to 1% weight change. They are, for all practical purposes, frozen. And this mechanism is critical because it explains why that initial fine-tune holds up over time. If your voice shifts slightly because of a cold or just aging, these core layers that just recognize human voice, they stay stable.
Which ensures the model doesn't suddenly revert to transcribing my speech as total gibberish.
Right. It preserves the structural integrity of the model.
Okay, so that's what's preserved. Where does the bulk of the actual specialized learning happen?
That happens in the later stages, the decoder layers and the output projection layer. These layers handle the high-level cognitive tasks, the language modeling, so predicting the next word based on context, and the specific mapping to vocabulary tokens. This is where your code-switching patterns and your custom technical glossary actually live.
And these layers see significant updates because they have the highest error rate on the fine-tuning data.
Precisely. These layers get the big updates, anywhere from 5% up to 30% weight change. So what we're doing is surgically altering only the parts of the model that control specific language prediction and vocabulary mapping.
And by limiting the change to just these highly specific task-relevant layers, the stability of the overall general ASR capability is maintained.
Yes. The stability over time is built right into this layer-wise differentiation.
That's an incredibly efficient use of training data. You're not wasting compute power trying to reteach the model how to recognize an S sound. You're just teaching it how to spell gRPC and where to place a Hebrew word.
You've got it.
Okay, Let's talk about how you assemble that training data. If I'm trying to teach the model a really complex, unknown technical term like some obscure library name, my intuition, maybe based on old school data science, would tell me to just record that word in isolation 50 times. Maximize the signal-to-noise ratio for that specific term.
Mm-hmm.
Why is that intuition totally wrong for modern ASR fine-tuning?
That intuition, while it's logical for isolated signal analysis, it just fundamentally misunderstands how modern neural language models actually learn.
Mm-hmm.
In this context, you should never minimize the surrounding context. Context is absolutely vital for generalization and for accurate learning.
But why would I include known words like I used the function or we need to install the, which the model already handles perfectly? Doesn't that just dilute the learning signal for the unknown word?
No, it doesn't dilute it because of how gradient focus works. When the model processes a full sentence, the loss function calculates the error across every single token. However, the magnitude of the gradient, that's the signal that tells the model how much to change its weights, is orders of magnitude higher for the tokens where the prediction error is large.
So the model intelligently ignores the words it got right and just hyper-focuses all its learning on the words it completely failed to predict, like the Hebrew mekalet or the term gRPC.
Exactly. The learning is concentrated precisely where it's needed most. But there's a second, even more critical reason for using full sentences, and that's co-articulation.
Right, the blending of sounds.
Speech is not a sequence of isolated sounds, it's a fluid stream. When you say, I went to the mekalet, the sound of the word the changes slightly when it's immediately followed by mekalet versus when it's followed by the word store.
So if I only train the model on the isolated word mekalet, it only learns this one very specific, very clean acoustic profile that might never actually occur in my natural speech flow.
Precisely. Natural sentence context is crucial because it teaches the model how your target words sound when they are blended with the speech around them. It accounts for those co-articulation effects that are unique to your cadence and your accent.
So it prevents the model from only recognizing the word in some kind of artificial isolation. It learns to handle the messy transitional acoustics of real conversation.
It does, which makes the data collection process clear. You record natural, full sentences.
And what about the language model part of it?
Well, the full context provides what we call contextual embeddings and strong language model priors. Training on varied contexts, like I'm going to the mekalet, I bought milk at the mekalet. It creates these richer, more generalized representations of that term. This helps the model disambiguate similar-sounding terms, and it learns the probability of the word's appearance.
It learns when in a sentence mekalet is a plausible prediction.
Exactly. It maximizes the model's confidence for your specific usage patterns. The sources are really consistent on this. Record natural conversational flow with maybe 10% to 15% density of your target vocabulary, but never isolated words.
We've established that fine-tuning is stable, it's necessary, and it addresses the core stability concerns. Now, let's get practical about deployment. Our listener has an AMD 7700 XT GPU. This means they are, resource constrained compared to a massive data center, but they still have decent local power.
Mm-hmm.
So should they fine-tune a massive model and run it expensively through a cloud API, or fine-tune a smaller model, like a smaller or tiny KitchMe, and run it locally for speed and privacy?
For a high-volume personal daily user, the answer leans overwhelmingly towards the local, fine-tuned, smaller model, and this all hinges on a concept called the crossover effect.
Okay, explain the crossover effect. Why does customizing a small, generally less accurate model give you a relatively larger accuracy gain than customizing an already accurate large model?
It's all about capacity utilization. A smaller model, like Whisper Small, it starts with a more significant inherent error rate because it has less capacity to generalize across all 680,000 hours of that audio data.
Right.
When you fine-tune that small model, you are dedicating all of its limited capacity to your specific niche. You're essentially telling it, stop worrying about Russian accents and niche dialects in Spanish and focus 100% on Israeli English, Hebrew code switching, and my technical glossary.
You're trading universal coverage for hyper-specific mastery.
Precisely. And we can use some concrete numbers from the research here. Stock Whisper Small on the listener's highly specific audio might give you a 12% to 15% AR. After just 10 hours of dedicated fine-tuning, that WEAR could realistically drop to 6% or 7%.
Okay. And where would a bigger model land?
Well, now you look at the stock, out-of-the-box Whisper Medium running without any fine-tuning, that might be closer to 8% AR on their specific profile.
So the fine-tuned Whisper Small at 7% AR is now effectively matching or even beating the stock whisper medium at 8% ER, but specifically in the user's domain.
That is the crossover. And the benefits of that are massive and practical. This equivalence means the user gets all the advantages of running the smaller model.
Which are?
Faster inference speed small is significantly quicker than medium, uses less VRAM, lower power consumption, and complete privacy because the data never leaves their local machine. For high-volume daily use, like taking notes or drafting documentation, these benefits of speed and privacy just overwhelmingly outweigh the marginal 1% or 2% accuracy gain you might get from a stock large model running on a paid cloud API.
Yeah, the cost and the latency of relying on the cloud for that last tiny bit of accuracy is just not worth it for the typical user. Local, fine-tuned small is the strategic winner.
And since we're deploying locally for that speed and privacy, we can't just use the standard PyTorch model format. We need models that are optimized for inference speed and specific hardware. So converting the model format is mandatory.
Okay, let's detail the optimal format for the listener's desktop GPU. They want the fastest possible transcription speed with their AMD 7700 XT.
For desktop and server environments where you're prioritizing speed and high throughput, the gold standard is the C-Translate2 format. This format is specifically designed for optimized inference with minimal latency, and it's used by libraries like Faster Whisper.
And how does it get that speed?
C-Translate2 achieves these speeds, often 4x faster than the original PyTorch model, by aggressively quantizing the model weights and optimizing the computational graphs for parallel processing on GPUs. And importantly, that includes the necessary support for the AMD ROCm ecosystem.
Okay, that handles the desktop. But what if they need to use this personalized accuracy on a more constrained device, like their phone or a single-board computer?
For those edge devices, the preferred format is GGUF, which stands for GPT Generation Unified Format. It evolved from the older GGML format.
What's it good for?
GGUF is optimized for CPU inference and for highly constrained memory environments. So if the user fine-tunes a tiny model, which is already very fast, and converts it to GGUF, they get a high degree of speed, total privacy, and full-on device operation. It's ideal for mobile dictation, where you don't want to rely on a network connection.
So the strategy is pretty clear. Fine-tune small with C-Translate2 for max desktop speed, and fine-tune tiny with GGUF for ultimate mobile privacy and portability. The deployment choice is just dictated by the hardware target.
Crucially, we need to address the listener's specific hardware, that AMD RX 7700 XT. For years, the inference world was completely dominated by NVIDIA's UDIA, which made life pretty miserable for AMD users. The listener needs the right tools to access that GPU power.
So what specific engine guarantees the best, most reliable ROCm support? ROCm being AMD's equivalent to CUE.
Based on the current tooling landscape, the recommendation is really unequivocal. Faster Whisper with its C-Translate2 backend. The sources confirm this combination has the most mature and reliable ROCm compatibility for these ASR workloads.
What about other alternatives?
Many other popular alternatives, like the initial PyTorch implementations or even some community projects like certain versions of Whisper.cpp, they often still silently default to CPU processing when they encounter AMD hardware, even if the user thinks their GPU is engaged.
That is a key pain point for AMD users, the silent CPU fallback. So if the listener is seeing poor performance, they need to check their utilization and probably switch to Faster Whisper.
Absolutely. That's the action plan for getting proper acceleration. And on that note about GPU utilization, seeing your 7700 XT spike to 100% during transcription burst is not only normal, it's highly desirable.
Right, it means the hardware is working.
It just means the hardware is efficiently processing the audio segments as quickly as it can. The only real measure of performance is what's called the real-time factor, or RTF.
And define RTF for us.
RTF is just calculated by dividing the time it took to process the audio by the duration of the audio itself. So an RTF of 1.0 means it took 60 seconds to process 60 seconds of audio. That's real time. An RTF of 0.1 means it transcribed 60 seconds of audio in just 6 seconds.
Very fast.
Very fast. So that 100% GPU utilization is only a bottleneck if the resulting RTF is slower than you want. If you can process a 1-hour meeting in 5 minutes, those 100% spikes are just signs of efficiency.
We focus a lot on the ASR model itself, but when we use a modern speech-to-text app, we get this clean, polished, ready-to-read document. And that output isn't generated by just one model.
Yeah.
So let's look under the hood at the entire production pipeline, this hidden symphony of models that makes transcription truly usable.
This is a crucial distinction. The ASR engine is just the heavy lifter. A functional professional transcription service requires a minimum of 4 models, all orchestrated in a very strict sequence.
So what's the very first step in that sequence, and how does it save computational power?
The initial component is the voice activity detection model, or VAD. This is often a very small, specialized neural network, maybe only 1 to 5 megabytes in size, which makes it extremely fast. Its only job is to filter out non-speech segments, silence, background noise, music. It just determines when speech is present.
So the VAD model runs first, and only the segments that it identifies as speech get passed on.
Exactly, and this is paramount for efficiency. For a 1-hour recording, VAD might filter out 20 minutes of total silence. That reduces the computational load on the massive ASR model by 30% right off the bat.
So the ASR model, our fine-tuned whisper, is the second component. It takes those clean speech segments and generates the raw, unformatted text. What happens next?
That raw text feeds into the post-processing phase. The most critical post-processor is the punctuation restoration model.
But wait, I thought Whisper could already do punctuation.
It can generate basic punctuation because its training data was punctuated, but it often misses complex capitalization, acronym formatting, and long-range punctuation rules. So dedicated models like deep punctuation or other custom fine-tuned NLP models specialize only in analyzing that raw text output and applying sophisticated punctuation and capitalization rules.
So the final clean, capitalized text is a blend of Whisper's initial guess, which is then refined by a second dedicated NLP model that runs right after.
That's the architecture for high-quality production text. And if the app involves multiple speakers, the pipeline includes a fourth component, diarization, which identifies and labels who is speaking when, speaker 1, speaker 2.
Okay, so the final quality really relies on this swift, sequential orchestration of VAD, ASR, punctuation, and diarization.
It does.
Understanding that symphony leads us to the fundamental difference between live or streaming, transcription, and file-based, or batch transcription. Why is transcribing a pre-recorded file fundamentally and architecturally just better in terms of accuracy?
It all comes down to constraints, specifically time and context. Live transcription operates under these non-negotiable constraints. It has to process audio incrementally. It has to maintain a fixed low latency so you see the words almost immediately.
And it's limited in context.
Fundamentally limited. It can only look backward, usually a maximum of 30 seconds of prior audio. So it's forced to make transcription and segmentation decisions on these incomplete chunks of information the moment I pause.
The live system has to commit, even if the rest of my sentence would have clarified a word I just used.
Precisely. Batch processing, on the other hand, just throws all those constraints out the window. It has several advantages that are impossible in a live setting. First is full bidirectional context.
It can look both backward and forward in time.
Yes, it can analyze the full audio segment, and this is invaluable for disambiguation. If the model isn't sure if you said do or do, knowing that you mentioned climate, 10 seconds later heavily biases the prediction toward do.
That kind of retroactive correction is completely impossible in a live stream.
It is. Second, optimal segmentation. Batch processing tools can analyze the entire file and optimally segment the audio at natural linguistic and acoustic pauses, rather than just cutting mid-sentence at some arbitrary time limit. And third, batch allows for multi-pass error correction and comprehensive audio pre-processing, like aggressive noise reduction that would just be too slow for a live stream.
Okay, so what's the quantifiable difference in accuracy?
Due to all these architectural advantages, the full context, the optimal segmentation, the relaxed latency batch transcription consistently yields an expected 5% to 20% better word error rate than live streaming.
Wow. So the implication for our listener is vital. If they've achieved a personal fine-tune down to 5% ER, they should be using batch processing on their recorded audio to make sure they capture that full accuracy potential.
Absolutely. Rather than relying on live transcription for their critical notes.
We've covered transcription, punctuation, and diarization. But for professional documentation, structure is everything. Why is logical paragraph creation the persistent, still unsolved frontier for these ASR models?
It's because paragraph breaks require a much higher level semantic understanding, what we call discourse segmentation. And that is fundamentally different from the acoustic modeling that Whisper performs.
It's a different kind of task.
A completely different task. Whisper is excellent at generating a stream of text that matches the audio, but it fails at adding logical grouping because that task depends on detecting topic shifts, tracking arguments, and recognizing rhetorical units.
And its training data, which was mostly just short, time-segmented captions, it never taught it those rules.
Exactly. The training data provided acoustic boundaries and sentence boundaries, the punctuation, but not discourse boundaries, the paragraphs. And what's more, paragraph rules aren't universal. A logical paragraph break in an email is very different from one in a legal brief. ASR models just don't have that global, high-level semantic awareness to make those complex, subjective decisions.
So if the ASR model outputs a clean, punctuated wall of text and the user needs structure right away, what's the best current workaround?
The workaround is to move the output of the ASR system immediately into an external large language model, or LLM. It's a separation of duties.
The ASR model handles the messy acoustics. The LLM handles the high-level writing and structure. The LLM becomes the semantic editor.
Correct. The user passes the raw transcript to an LLM like Claude or GPT with a specific formatting-focused prompt, something like, take this raw text and format it into a professional summary, ensuring you add logical paragraph breaks and use headings where topics shift.
And the LLM can do that because it was trained on billions of structured documents. It understands logical grouping and semantic flow.
Far more accurately than any current dedicated ASR pipeline component can. This LLM post-processing step is the current, most reliable solution for turning raw ASR output into truly usable structured text.
This deep dive has provided a really clear roadmap for anyone looking to personalize their speech recognition workflow. Let's just synthesize the key findings for our listener.
First, personalized fine-tuning is absolutely validated, especially for those highly specific challenges like code switching, complex accents, and technical terminology. The ROI is undeniable. It transforms the system from merely acceptable to genuinely trustworthy by crossing that critical usability cliff around 5% ERR.
Second, and I think most importantly to the core question, your fine-tune will last. The architectural stability of modern ASR models is extremely high. That combination of low learning rates and layer-specific updates ensures that the vast base knowledge stays intact, while only the specific late-stage language modeling layers get adjusted.
Which makes the model robust against the natural, gradual changes your voice will experience over many years. This means large, continuous retraining is unnecessary.
Third, for practical deployment on your AMD 7700 XT, the path to speed and privacy is local, not cloud-based. You want to focus on achieving that crossover effect by fine-tuning a smaller model, like Whisper Small.
And deploying that model using the Faster Whisper engine and the C-Translate 2 format guarantees high speed and the best, most reliable utilization of your AMD hardware.
And finally, remember that usable text is a multi-model effort. You'll maximize your personal accuracy by prioritizing batch transcription over live streaming. And you should be prepared to rely on a powerful large language model as a separate post-processing step to get those complex, missing features like logical paragraph breaks.
Now for our final thought. We've established that ASR is rapidly integrating into these unified foundation models, moving way beyond simple transcription. Early ASR systems were rigid. They were just trying to transcribe what was said. We are now moving into models that analyze how it was said, detecting emotion, tone, prosody, and integrating that analysis into the output.
It's moving from just text generation to complex semantic analysis.
So if future models treat speech documentation not as a one-off tool, but as a continuous platform, one that's constantly learning, identifying conversational trends, maybe even inferring intent, how might these highly personalized deep learning systems fundamentally change our reliance on memory, on note-taking, and even the basic requirements for verbal communication in a world where every conversation is documented, structured, and analyzed in real time?
That is certainly something to ponder as these models become our co-pilots in basically every conversation. Thank you for joining us for this deep dive into the stability and future of personalized speech recognition. We'll catch you next time.